The purpose of this conference is to bring together experts in environmental issues and behavior analysts whose expertise is behavior change. So welcome to the conference. It's been a real joy to work with a wonderful group of behavior analysts from across the states and several foreign countries who've come together as a program committee to plan this conference for you. All of the members of the committee are here. I see most everybody already in the room, save for one, our colleague Paul Chance, who just recently moved from Maryland to Japan and is in the middle of building a home. And Paul very, very much wanted to be here, but he's in here with us not only in spirit, but in his contribution to this program in so many, many ways. Now, I mentioned that all of the rest of the committee is here. I want you to know that and look for name tags so you can find them. If you have any problems during the conference whatsoever, feel free to speak to any of them. I'll be busy. This conference could not take place, nor the program and the facilities and our opportunities to learn together at anywhere near the level that it has and it will be without the support of a number of great organizations in sponsoring and co-sponsoring this conference in a variety of ways. Among those sponsors, The Ohio State University has really stepped up to not only provide support in the very real and important areas of finance to help us pull this off, but in the program area as well. And among those sponsors, the Ohio State Office of Energy and Environment has been at the forefront in many, many ways. It's my pleasure now to introduce to you Dr. Ronald Sega. Dr. Sega is director of the Ohio State Office of Energy and Environment. He also serves as University Vice President for Enterprise Executive for Energy and the Environment. He holds that job. He does it so well, or apparently in his spare time so easily, that he has the job at Ohio State and at Colorado State University. Interesting how that happens. Dr. Sega holds a bachelor's degree in math from the U.S. Air Force Academy, his master's in physics from OSU, and a PhD in electrical engineering from the University of Colorado. He served as Undersecretary of the Air Force from 2005 to 2007, leading the team that won the 2006 Presidential Award for Leadership in Federal Energy Management. From 2001 to 2005, Ron served as Director of Defense Research and Engineering, the Chief Technology Officer in the Department of Defense. After 31 years of service, he retired from the Air Force Reserve in 2005 at the rank of Major General. One of a very few number of people who have had the opportunity to peer out of a window in the space shuttle and view our beautiful Earth from above. Dr. Sega is also an astronaut, and he flew aboard the space shuttles Discovery and Atlantis. Please join me in welcoming Dr. Ronald Sega.
Well, thank you, Bill, for that kind introduction, and it's really a pleasure, honor, and privilege for me to be here. And on behalf of President Gordon Gee, welcome to The Ohio State University. I also share your comments with respect to the Office of Energy and Environment. We've got some great folks. Kate Barter and Gina Langen are here. I hope you'll get a chance to say hello to them during the reception. See what we have up here. Okay. Well, this is an important topic, sustainability. And I believe it's an important conference. I talked to the Dean of Arts and Sciences, Joe Steinmetz, and who is a participant in many of the Association of Behavior Analysts international conferences in the past, and so this is one of the, maybe the first time that a topic has been the center of focus for this association. So I think this is really important. And look forward to the results of the conference over the next couple days. As was pointed out, my title is Vice President and Enterprise Executive for Energy and Environment. And so we're looking at the topics of energy and environment as an enterprise. It's a multidisciplinary effort, energy, environment, and sustainability. It includes many facets, clearly, of this community at Ohio State. And the engineering fields are clearly there, which is kind of my background in science. But clearly the social sciences, behavioral scientists are key to us working and making progress in this large system of energy, environment, and sustainability. See how this works? There we go. Got sort of a block O there with sustainability. And this is a definition. I kind of like it. It's from a UN conference in 1987 where sustainability is defined as meeting present needs without compromising the ability of future generations to meet their needs. Now, each individual entity, function, organization, group at Ohio State is working hard on this. Some are doing global research in the polar regions. Our students are probably leading the way in many ways in the area of sustainability, and kind of harken back to some activities in the past where not many people wearing seat belts. And by and large, the folks in front of the car, mom and dad, start wearing their seat belts more because the folks in the back of the car, the kids, were saying, Mom, Dad, put your seat belt on. And pretty soon behavior starts to move along, one generation encouraging the other. Also, I grew up in northeastern Ohio, and it was not uncommon to have trash being thrown out of cars and so forth, bottles and cans and so forth. And pretty soon it became not the thing to do as one went along, is to litter the highways. And then we have areas of outreach, laboratories, the infrastructure, government, all working on sustainability. But it's important, we think, is that white dotted arrow that runs around the block O is the integration of these activities. And if we do that in an integrated way, I believe the tide, if you will, rises and takes all boats with it. And therefore, the arrow is going back out of the block O. Kind of a view of looking at sustainability in a systems way and integrating the various functions we have at Ohio State. So one of my tasks in my past was, as the Secretary of the Air Force, I was in charge of the space programs for the Department of Defense, research and development in the Air Force, and I was the energy executive. And so we looked at creating an energy strategy, and the vision was make energy a consideration in all we do. So that would mean turning the lights off when you left, but if you were responsible for buying something, acquisition, procurement, you would think about the life cycle of the system you were purchasing and making energy a consideration how you went about making that decision. So we looked at supply for energy, demand on energy, and culture. Three big elements: supply, demand, culture. Looking at alternative sources for fuel for airplanes, alternative sources of energy for our infrastructure, our buildings, renewables, for example. Energy efficiency, working on doing operations in a different way. But by and large, the savings, especially in the first couple years, came primarily from culture behavior change. So we looked at what we did in different parts of the country, different parts of the world. We would try to take advantage of what was out physically. For example, up here in Wyoming, the wind blows all the time. You get out of the airplane, just ask the folks, wind blow like this all the time? They go, all the time. Probably a good idea to put a wind turbine up there. Same question down in Las Vegas, over here. And the sun's shining a lot. Put in the largest solar farm in North America at the time in conjunction with the community. Also, when you're driving on the bases, the speed limit is 25, 30 miles an hour. Why buy a vehicle that goes 120 if something that goes at lower speed is more efficient and effective? And so at each point, we all not only had physical attributes, but the cultures are a little bit different in different parts of the country and what the folks are actually doing. So that came into play of how we would try to optimize our work and efforts in the energy space. So we end up doing pretty well. We won Green Power Partner of the Year Award, Climate Protection Award, Stratospheric Ozone Award, and as was pointed out, the overall award for Presidential Award for Leadership in Federal Energy Management for the U.S. government. Saved 3.3 trillion BTUs of energy in 1 year, fiscal 2006, enough to power 100,000 homes. Primarily due to behavior change, culture change that was evolving during that year. So as we look here at Ohio State, we're trying to integrate the various functions that university does. In this case, it's a pretty big university, 65,000 students, maybe 100,000 people on the campus in a given working day. So it's a little city, and we clearly do research here. We have academics, student life activities, campus operations. It's important for us to address energy and environmental policy. Come on in, folks. Land grant, mission, and outreach is part of what we do here at Ohio State. And the question is, how are they connected? When we build a building, we want it to keep you warm in the winter, cool in the summer. But we also want to look at it, how it operates, that it's not only efficient, but it's kind of part of our classroom environment. Instrumented, so it's part of a test bed, a laboratory that extends throughout the campus. How we actually work and operate it is also important. Not only do we want to have it built and designed correctly, but we don't want to have the door propped open in the middle of the winter and our lead sign outside, and it's obviously not working very well because of behavior. So some examples, as we look at the campus, from above, it's hard to tell what functions are going on in buildings, whether it be research or academics or dorms out there. And so we're working hard on integrating all these pieces. So the students will learn in the classroom as well as have a experience while they're here at Ohio State. So whether it be some of the technical things in terms of smart grid work and smart metering, which may feed back into how we actually live and work here, to commercial activities such as the battery testing you see out there. So student groups are very, very active. We have, 20, 30 or more student groups in this area. They think before you throw event is something that the students obviously are leading. River Cleanup Day at the Olentangy River. We also are instrumenting buildings, so we kind of know how they function physically and what the energy demand is in them, but it also provides a feedback mechanism of what we are doing in the building, and we're going to do more and more of this as we look at new dorms and so forth, so that feedback into how we live and act while on campus. About 8 of the buildings are instrumented real time. The other ones are a bit slower in terms of getting feedback. So campus waste minimization is a big, big deal. We have a common look to all of our recycle cans, so people know them. They're everywhere, and that's helping an awful lot in terms of how people are interacting and recycling. This solar compactor is another example, and a food pulper in our area for food services. Even athletics. So the messaging through athletics, we had a zero waste approach to recycling and diversion, and moving into the 70-80%. Last graduation was into that same range, so making really good progress on a large scale. In this case, for those that are familiar with the recycle formation, these are kind of the arrows. There's arrow there, and it's the recycle symbol as we have these arrows interlocked in the recycle formation. So messaging and everything we do is important. So also, it was mentioned that I got a chance to fly in space. So as the shuttle's going off, it is a big team of people that had to be responsible for it going off. A really small group of folks actually flying in space. Large group supporting it during the launch operations, as well as on orbit and in the re-entry and landing. An even larger group that's responsible for the experiments and setting up the shuttle and all those kinds of things. Once in space, you're there, you can't go very far. And especially for longer duration flights, the psychological aspects and the interrelationships among the crew members is very, very important. Our leader was Charlie Bolden. He's currently the administrator of NASA in kind of the upper right-hand corner of that tunnel picture. Great leader, great people person. Maybe the tightest crew that I'm aware of that ever flew in the space shuttle was this one. Had Sergei Krikalev from Russia, first time he had flown a Russian cosmonaut. Franklin Chang Diaz from Costa Rica came to the United States to be able to go to space. Jan Davis, a PhD in engineering, and Ken Reitler's up in the upper part there. And so the crew that got along really well together in an enclosed space. We didn't listen apparently real well to all of our training, because right there is our little photo card that our trainers basically said put on the camera, but in this case it was clearly not there. Now, the picture on the right is Columbus. So we have the confluence of the Scioto and Olentangy River, and let's see if I'm going to get this right here as to where we are up in, this is downtown, I think, here. So we are right in this area. I should have focused on exactly where the Union was at Ohio State. But that's a view from the shuttle of Columbus, Ohio. And my final picture is this. Planet Earth, we didn't get to see this for exactly this vantage point. This is clearly from Apollo, from much further away than the view of the space shuttle. But you can see massive changes going on. You can see some of the deforestation that's taking place, some of the clear cutting and burning while you're in space. And you can see the difference of some of the pictures of what has happened over time from space, whether it be Oral Sea or Lake Chad, or some of the areas that our featured speaker has been absolutely a pioneer in making the key measurements on the Earth. Lonnie Thompson clearly has been at many places here on the planet. We had a chance to view it from above, but he has been on the ground and making key measurements and doing key analysis for all of us. And it's my pleasure at this time to introduce Lonnie as our featured speaker. Dr. Lonnie Thompson is an Ohio State treasurer and a torchbearer for climate change issues. A distinguished university professor in the School of Earth Sciences and a senior research scientist in our Byrd Polar Research Corps, paleoclimatology out of the polar regions to the highest tropical and subtropical ice fields. He and his Ohio State team have developed lightweight, solar-powered drilling equipment for determining histories from ice fields in the tropical South American Andes, the Himalayas, and on Kilimanjaro. The paleoclimate histories have advanced our understanding of Earth's climate. His observations of glacier retreat over the last 3 decades confirm that glaciers around the world are melting, and has led to his conclusion that the warming of the last 50 years is now outside the range of climate variability. Dr. Thompson holds honorary degrees from several prestigious institutions and has been awarded the Benjamin Franklin Medal, the Time International Magazine Environmental Hero Award, and the U.S. Medal of Science. He is an elected member of the National Academy of Sciences, a fellow of the American Association for the Advancement of Science, and a foreign member of the Chinese Academy of Sciences, among numerous other recognitions. It is my pleasure to welcome Dr. Lonnie Thompson to the Behavior Change for Sustainable World Conference.
Thank you, Ron.
Hope that was okay, otherwise it may be back to your freezer, huh?
That's right. You have to be careful. It's my pleasure to be able to speak here this evening. I first spoke at the 35th meeting of this group out in Phoenix, out of which there was a publication that I work with Bill Hayward on and Paul Chance. And I must say that we publish a lot of papers in Science and Nature. This is the most requested paper we have ever published. And I think it's because it reaches out to people with the message of climate change and what we might do about it. So what I want to talk about tonight is a little bit about glaciers and what's happening to glaciers around the world and how we tell about climate, but also my experience with human response because I've become more and more convinced that one more ice core is not going to change the direction that we're on, and we have to do something about human behavior. So I've been very fortunate to have been on 58 expeditions, 16 different countries. So I've been able to see a lot of ice and glaciers and how they've changed through time. It couldn't be done without a team, and we have a small team here at Ohio State, but they're very efficient, of professionals as well as graduate students, and you could not do this research without that team. So I want to talk about inconvenient truth, and this is kind of an introduction to global climate change, and then talk about glaciers as recorders of global climate change, and some examples of how climate change has impacted cultures in the past, and evidence for the recent acceleration in the rate of ice loss around the world, and evidence that in some cases these glaciers are smaller than they have been in at least 6,000 years. Then I'm going to speak a little bit about an inconvenient mind, and this to me seems to be a bigger problem, and I think B.F. Skinner tried to deal with this in his life, and there are a couple things that are very relevant to climate change. Immediate consequences outweigh delayed consequences. Well, when we talk about climate change, we're talking about 30-year averages of meteorology. So these are longer-term trends, and as human beings, we deal with the here and now rather than what might be happening tomorrow. And then the consequences for individuals outweigh consequences for others. We're more likely to respond to something that affects us directly than something that's affecting a group down in the Andes or over in the Himalayas. And then I want to talk about our greatest challenges as I see them from the 21st century. This is a quote that I really like. There are 3 stages to any scientific discovery. First, people will deny that it's true. Then they will deny that it's important. And then they will credit the wrong person. Now, what's interesting about this came from Alexander Humboldt 150 years ago. So it would say that human nature has not changed that much. So if we look at the mechanisms of climate change, there are natural mechanisms that have been changing the climate on this planet for millions of years. Some of the natural things are changes in our sun. We have a 12-year solar cycle. We also have a 90-year Glacier cycle. And so the energy received by the planet does change through time. There's changes in the amount of volcanic dust, aerosols, sulfates in the atmosphere, which can cool the temperature of our planet for 1 or 2 years after a major eruption. There's also internal variability in the system, things that drive El Niños, monsoons, and the like. So those are natural. And on top of this, we have the human influences, some of which are the changes in concentration of greenhouse gases. And there's a figure there showing the changes in CO2 as measured in ice cores, and then coming forward as measured by Charles Keeling in the atmosphere over Mauna Loa. Then there's changes in aerosols and particles from burning fossil fuels. There's sulfate aerosols, those will change albedos of the surface, black carbon emissions. Then there's changes in the reflectivity, the albedo of the Earth, as we clear land for more crops and people and animals to support those people. So these are tremendous impacts. Fortunately, we can actually use climate models to break out what you would expect to see from any one of those forcings. And I'll just point out a couple of these. If you were looking for changes in solar irradiance, and this is going from North Pole to South Pole. This is the troposphere where you live down here at the surface. This is the stratosphere, which is above there. These are heights in miles. If something changed on the sun, we would expect temperatures in the stratosphere and the troposphere to change in unison because the energy is coming from outside of the system. If we had a volcanic eruption, we would expect the stratosphere to warm because that's where the aerosols are concentrated, it absorbs radiation. Surface will cool because you're not getting as much radiation. If you were looking at greenhouse gas forcing, you would expect the troposphere down where we live to warm, whereas we'd expect the stratosphere above to actually cool. The beauty about this is that we can actually go out and see what's happened in our atmosphere, and this is a figure that actually shows that. You'll see that over this period from 1960 to up to the present, the temperatures in our stratosphere are cooling, except when there's a volcanic eruption. You can see that they warm, is exactly what the models would suggest. If you get in the troposphere, we see that at all levels, upper, lower, and down at the surface of the Earth, temperatures are warming. So the stratosphere is cooling, while the troposphere and the surface are warming in concert. This cannot be due to changes in the sun, and is predicted by our climate models. So if you look at the CO2 changes as measured by Charles Keeling, you can see that CO2 continues to increase. There has been really an acceleration. We're looking at about 2 parts per million to 3 parts per million increase now per year. We have in the ice cores a history of these greenhouse gases. They're trapped in the bubbles in the ice. In fact, the only long-term record we have of our composition of our atmosphere. And if you look at the longest record we have right now, goes back 800,000 years. And so this in blue is a record of CO2, and in red is a record of methane. So you can see there is a 100,000-year cycle in these. These are due to orbital forcings, long-term changes that cause changes of climate on this planet. If you go back 20,000 years, there was an ice sheet over where we're sitting right now. And if you look at CO2, it was about 190 to 200 parts per million by volume. During warm periods, when the ice sheets melt back, we're looking at about 300 parts per million by volume. So if you look at where we are today, we are actually over 390 parts per million by volume of CO2, and methane is about 1,800 parts per billion by volume. Concern is where we're projected to be by 2100, and certainly right now there's no analog in 800,000 years to where we are, but where will we be in 2100 at our current rates of emissions? We usually talk more about CO2 rather than methane, because methane only stays in the atmosphere 10 to 12 years, whereas CO2 will remain for decades to millennia. And this is an important problem when you're talking about climate change, because if we decided tomorrow to eliminate CO2 emissions to the atmosphere, the decay curve would look something like this. So 100 years out, you'd still have 33% of that CO2 in the atmosphere. 1,000 years out, you'd still have about 20%. So it has a long-term lifespan once it's emitted into the atmosphere. Charles Keeling passed away in 2005. This is the CO2 curve since his departure. And I checked this morning in Mauna Loa, the CO2 levels today are 395 parts per million by volume. So we can continue in this upward increase. Of course, the drivers of this can be tied to population and people. And this gives you an example of how rapidly the population of the Earth has increased. And what is really striking about this and makes our time different than any time in the history of our planet is there's never been 7 billion people living on it. So we're making a big difference. And then if you look at just some of the things that we need to live on this planet, you look at the support, the life support system. You know, in 2012, we have about 17 billion chickens and ducks and things that we need, 1.9 billion sheep and goats, and even 400 million dogs, 500 million cats. We are having a huge impact on this planet. So in contrast, you can look at, say, the pre-exploitation exportation number of American bison. We had only 60 to 80 million. So yeah, we're changing things drastically. And of course, you can see that. You can see that at night from space. These are the lights, and in today's world, about 65% of the electricity is coming from fossil fuels. And what's striking is the projections that you can see of what this world will look like by 2030 That's not too far off. This is from General Electric. And you can see the demand for electricity, energy, is projected to continue to increase. And the question is, what is that going to do to the atmosphere? And of course, that depends on the choices we make for our energy sources going forward. So how to manage a world of both rising energy consumption and rising climate threats becomes a major issue that we have to deal with. Now I want to talk a little bit about the climate side, and this is where my expertise actually lies. We are very fortunate to live on a planet where we have many recorders of the past, and they can give us a perspective on the 21st century that we can't get from our instrumental records and the like. And of course, we look at ice cores drilled from glaciers around the world. And we have the longest records of history coming from the polar regions, where we have the most ice, going back over 800,000 years. But we have relatively high resolution records coming out of the low latitudes. These are annual layers on the margin of the Kilkaya ice cap, photo taken back in 1977. And it's the change that's taking place that's so important. This is 1977. This is the same place in 2002. So you can see that there are two main issues here. We're losing a water resource in the glaciers, but we're also losing a history of the past that's recorded on these mountaintop glaciers. Glaciers can contribute in many ways to reconstruction of the past climate and history of the planet. We can look at everything from the temperature of the planet through measurement of stable isotopes of oxygen and hydrogen. We can look at atmospheric chemistry. We can actually see in the ice cores in Greenland when we put lead into gasoline. We can see when the Clean Air Act was passed and the lead was taken out. They're recorders of anything that's in the atmosphere. There's a history of precipitation that we cannot get from many of our archives. Just by measuring the layer thicknesses each year in these cores, we can get an idea of how accumulation has changed. But dustiness in the atmosphere, vegetation changes through pollen that's in the ice, volcanic history, the tephra and the sulfates, anthropogenic emissions, the greenhouse gases, all these things are in the ice. We can even look at entrapped microorganisms. So anything in the atmosphere, it can end up in the ice. These records are unique because they come from parts of the world where we don't have records. The very high mountain remote areas of the planet, the polar regions, so they can give us a perspective in places where we have none. Those of you who made the tour over at the Byrd Polar Research Center saw some of this, the clean rooms where the analysis are done, the mass spectrometers that do the stable isotopes. We have a storage facility where we now have over 7,000 meters of core stored at minus 30 degrees Fahrenheit. And we build and design and build the drills that we use in order to go to these very high mountaintops. They have to be lightweight, portable systems. And any other time in human history, you couldn't do this. We have materials so that we can do it in today's world. So over the past 30 years, these are the places where our team has drilled. So the whole idea is to get a global picture of climate of the Earth from ice. And then to put that together to look at how the system has changed. I think we often forget about the fact that we live on a sphere, and because of that, we have 50% of the surface of our planet is actually in the tropics, between 30 north and 30 south. And 70% of that 7 billion people live in that zone. So it's an area that we need to understand climate variation, both natural and human-driven. Turns out the tropics are a unique place on our planet. Surface temperatures of the ocean, dry precipitation, as you can see in this lower panel. But when you get up to 500 millibar level, where all the ice caps are located, temperatures are very uniform in the tropics. And so changes at that level become very, very significant. I'm going to take you to one of these sites just to give you an idea of how we get the records. I'm going to go down to Kilkaya ice cap. This is the largest tropical ice cap on Earth. That's right above the Amazon basin. It is at an elevation of 5,670 meters and in a remote part of the Altiplano in southern Peru. If you make your way up to the summit of the ice cap, you can see the drill dome up here. It's a huge body of mass to be 9 degrees south of the equator. The ice cores are drilled. This is what they look like when we were collecting them in the field. And if you look into a crevasse on this ice field, you can actually see every dry season. There's a wet and dry season here. Dry season, you get dust. If you go down into the crevasse, you can actually see how uniform these layers are. And if you measure the thickness of between those, then you have accumulation, the history of the past. So if you bring the ice cores back, you can analyze the history of temperature, our isotopes shown here, and of the dust. And every year, every dry season, there's a dust layer. So you count these like you would a tree. So this is 1805 to 1825. We can go back in time. And you'll notice as you go back in time, time gets compressed in an ice core. But you still can see each year. The Spanish arrived here in 1531. So the first records that we can actually interpret from that part of the world come with the written record after that. But the ice core allows you to go back far before that. This is 1240 up to 1330 AD. So we can go back through the rise and fall of the Incas and the Wari cultures and look at what role climate played in those societies. Just to give you an idea of the reproducibility of these records, this was the first core that we drilled out of Kilkaya back in 1983. We had no way to keep cores frozen at that time. They came back 6,000 bottled water samples. These isotopes, these are decadal averages for the last 1,000 years. We went back in 2003 and redrilled this ice field because we now know it's the largest ice field on Earth, and brought back frozen ice core, which are over in the freezer here at Ohio State. But you can see the reproducibility of the record. You can see the Little Ice Age, the blues here. You can see the warming in the 20th century, and you can see how that warming has extended as we've come over the last 20 years. We can also look at precipitation history over that same time periods. The browns are periods of a lower accumulation, the blues are higher. And you can look at the 20th century and you can see that it's wetter than average. So it's warmer and wetter in this part of the world. Now, there's a huge record of cultures, archaeologists and anthropologists working in this area. This is Machu Picchu, part of the Inca Empire. And you can actually look at the history coming from the ice core. And we'll just look at the precipitation here. Browns are when it's dry up on the Altiplano in southern Peru. Blues are when it's wet. And you can see there this oscillates through time. And if you look at the history of cultures, you see they also oscillate through time. And so if you look at the first period here with the Mochi culture, it's dry up in the highlands. People are living down on the coast, and the capital is on the coast. When it becomes wet or wetter in the highlands, the cultures move to the higher elevations. The capital actually moves to higher elevations. And then when it becomes dry again, you see people moving back to the coast, and the capital moves back to the coast. And then with the rise of the Incas in this latest wet period here, we have extensive development, the highlands in Peru. And of course that came to the end when the Spanish arrived. But it's interesting to look at that history in terms of the last 100 years on this record, because the last 100 years shows that it's been wetter than average. And yet if you look at population dynamics, people have been moving out of the highlands to the coastal areas where the capital is, Lima, out in the middle of the desert. 10 million people. People are looking for a better way of life. And the question is whether this movement of people into water-sparse areas is sustainable on the long term. Certainly, if you look at the history of populations, they've been moving from the highlands to the lowlands in sync with changes in precipitation. Well, we can take these records from around the world and look at what's happened in the last 2,000 years of temperature as recorded through the isotopes. These are decadal averages coming up to the present, and you can see the rise in the 20th century. And we can compare that to changes that have been measured in other archives. These are tree rings in the northern hemisphere, and this is our instrumental records right here at the top. And what stands out in these records is what's happened in the last 50 years. Now, glaciers record a history inside the ice themselves, but they also respond to the changes in the climate. And as it warms, these glaciers are retreating. And if you look at this photograph taken in 1977, this is all now a lake in this part of the world. And in 2002, this is the backside of that lake. You can see a person for scale, this 30-meter high mountain or ice wall. And this is a plant. It's a wetland plant, no woody tissue, perfectly preserved. And it came out from the retreating margin. You see the margin of the ice here, and here's the plant. And these plants can be collected and dated. But what's amazing is how fast the ice is retreating. This is in 2002. This is the same place in 2005. And these are the plants that were just coming out. So this whole wall continues to retreat. We've now collected over 60 specimens of plants as this retreats. This particular plant was Deciduous muscoides. This is what it looked like in the archive. This is what it looks like in the modern day world. But there's no woody tissue. If these are exposed, they will decay. And so these tell us that this glacier hasn't been smaller for over 5,000 years. Otherwise, these plants wouldn't be there. And we continue to make these collections. These are all plants. I mean, it's amazing. There are truckloads of plants that are captured by this glacier. And this is in 2003. This is the same place in 2011. There's new land being exposed as the glacier retreats, and the 5 plant samples collected here last year date over 6,300 years. So we know this glacier hasn't been smaller for at least 6,000 years, otherwise these plants wouldn't be there. So I think nature's best thermometer, perhaps its most sensitive and unambiguous indicator of climate change, is ice. And this is a quote from Henry Pollack's book, A World Without Ice. Ice asks no questions, presents no arguments, reads no newspapers, listens to no debates. It's not burdened by any ideology, and it carries no political baggage. As it changes from a solid to a liquid, it just melts. And so I'm going to take you very quickly around the world to show you what's happening to glaciers. This is up in Brooks Range. It's the McCall Glacier. Photo from 1958, same place in 2003. 100% of the glaciers in this mountain range are retreating in today's world. And when you look at the glaciers, just think of them as water on land. When they melt, they go into the world's oceans. This is southeast Alaska. This is the Muir Glacier as it appeared in 1941 on the left, and in 2004. It was, in 1941, it was over 800 meters thick. 98% of the glaciers in southeast Alaska are retreating in today's world. If you go to the Himalayas, it's hard to find old pictures, but here's a picture of a glacier as it appeared in 1921. Here's the same place in 2009. And you see the glaciers way up here now. So huge changes. Of the glaciers measured in this part of the world, there are 46,000 of them. Of those measured, 95% of them are retreating. If you go to the Alps, we have some older pictures from there. This is 1903, and this will fade into 2005 to show the loss of ice in that area. 99% of the glaciers in the Alps are retreating in today's world. If you go to the tropics, where we spend a lot of time, 100% of the glaciers in that region are retreating in today's world, the ones we have measurements on. On the Quelccaya ice cap where we've worked, we've been monitoring the Coriocalis Glacier since 1978. In 1978, there was no lake in this valley. This is the same place in 2008, and you can see there's an 84-acre lake that is formed. It started forming in 1991. The problem is that these are not single glaciers that are responding to these changes. This is a Landsat image taken in 1988 of this area. This is the Quelccaya ice cap, and this is the Cordillera Vilcanota. And then you can compare it to a Landsat from 2006, and you can see the lake that's formed in here on the Corey-Calyx Glacier. But if you look at the change, the area loss over that period of time, all these yellow areas, up here in the Cordillera Vilcanota, we have lost over 24% of the area of ice over this very, very short period of time. And of course, this is a loss of water resources in that part of the world. We also work in Tibet. We've been working in China for over 30 years now, and drilling ice cores from that part of the world. And we have 5 different sites. I'm only going to mention this one because it sits at the source of the Indus River, the Ganges River, and the Brahmaputra River. And these are all very important water resources for people who live in that part of the world. This is what the mountain looks like if you go there. And if you make your way up through these canyons, you'll come up to the Nanunami Glacier. And if you get to the top of it, this is what it looks like. And we drilled 3 cores of bedrock. The deepest is 158 meters. When the cores come back from all these places, the first thing we measure is radioactivity. All the thermonuclear bomb tests that humans have put out in the atmosphere have left a radioactive layer on all the glaciers of the world. So if you drill them, you can measure them, and these are the first 4 sites that we drilled. This is from the Soviet tests in 62, 63, beta radioactivity. But when we got to the latest site, these are the dates they were drilled. And, there is no 1962 event. And then we look for an earlier test. We look for the Ivy test. It's recorded in chlorine-36, and you can see it around the world in these different sites, only you don't see it on Nanunami at the top of the Himalayas. And the reason you don't see it is the glacier is wasting at the very highest elevations, over 20,000 feet from the surface down. So we're losing, it's not accumulating in today's climate. And this has tremendous implications for water resources and the rates of change in that part of the world. We've also been working on Kilimanjaro since 1999, but the first photo was taken in 1912. This shows the amount of ice that was there in 2006. So about 85% of the ice that was on the mountain back in 1912 is now gone. And we know that loss continues because we continue to monitor it. This is the Furtwanger Glacier in the crater here. This is a photo from 2000. 2006, you can see it's dividing. By 2007, it has split in 2. And the problem is there are positive feedbacks here. Once you remove this white surface, you're exposing a darker bedrock, which absorbs more energy, increases the heat, the glacier melts faster. So you get into these positive feedback loops. And this is a GeoEye image of Kilimanjaro taken in 2010 in August. And Furtwanger here is now in 3 pieces, and the northern ice field will soon split in 2. So the loss of ice there continues. So the last place I want to show you for glaciers is in New Guinea. Most people don't know that there's glaciers in New Guinea. There's only one ice field between the Himalayas and the Andes, and it's near Putrajaya here in New Guinea. If you look at the ice loss here, this is what the glaciers looked like back in 1936. 1991, they had broken up into pieces. This was in 2001. We went here to drill this site in 2010. And this is what the glaciers look like. And you see they're ablating. These glaciers are losing mass from the surface down. They will soon disappear from this part of the world. And to give an example of that, we drilled for 2 weeks. There was a tent setting right here. And you can see it's now on a platform because it rained every day. And the surface of the glacier is lowering from the top down. And that's 30 centimeters. The glacier is only 32 meters thick. So you can see that in 5 or 6 years, this glacier will be history. And the only ice will be over in the Byrd Polar Research Center in our archive. This shows the areas we drilled on this dome and up on the dome here. So if you were to look at the glaciers throughout the tropics, doesn't matter whether you're in South America, Africa, and the southern Himalayas or over in New Guinea, they all show an acceleration in ice loss as you come to the present day. And this is a concern when you talk about water resources. So how do climate changes impact humans? Well, if you live in these areas, you can already see those changes taking place. This is a lake that existed and for years water flowed to the north. This is in 2006. In 2007, it had drained. And if you go around this bend, the water is now flowing underneath the glacier into another valley to the south. And if you happen to graze your alpaca in the North Valley, all the vegetation has died, and you no longer can do that. There are geologic hazards forming as these glaciers melt. This lake started forming in 1991. This is July of 2005. There was an avalanche that came off of this peak here. It fell into the lake by 2006. And you can see all the debris covering this meadow, and alpaca were drowned. And the point here is this would not have happened before 1991 because there was a glacier in the valley, and anything falling off the top would have just fallen on ice. But these are new hazards. The people who live in these areas, the Quechua Indians, live right on the edge anyway when you talk about survival. So these changes have tremendous impacts on them. If you look at the bigger picture in the 20th and 21st century, all those red areas you see are places where we're losing ice on the planet. And it's interesting, if you look at that, it's very clear that we are now climatologically in unfamiliar territory, and the world's ice cover is responding. And I think this is one of the first responders that we have in our climate system to climate change. But it's interesting to ask the question, what if we lose 8% of the ice that we now have on land? How would that impact sea level? 8%, I mean, that's not exaggerating. So if you look at our coastal areas of the Gulf, New Orleans, down here, Florida, and you say, what happens if you lose 8% of the ice on our planet? This is what it would look like. So a lot of the major cities would be gone. And so this is the real concern, is that these glaciers cover 10% of the surface of the planet, but they're in remote places. But that water goes into the oceans, and that affects the world as a whole. So can nature change an inconvenient mind? And it's interesting to look at the losses. This comes from Munich Re. And here you're looking at, these are major natural disasters, and they include earthquakes, which are in red, meteorological events, which are in green, hydrological events, and then climatological events, which are in orange, that are due to extreme temperatures or droughts or wildfires. And if you look at this from 1980 to 2010, you can see this increasing. So it raises the issue of whether V.F. Skinner might actually be right in human nature. Immediate consequences outweigh delayed consequences. And all you have to do is look at what has taken place on this planet in the last couple of years to see the extremes that we have had in the weather. This is in Chicago in February of 2011. This is down in Alabama, the tornadoes that occurred in 2011. This is out in Joplin, Minnesota, or Missouri, and this is in 2011. And if you look at the number of lives lost due to weather in 2011, these are tornadoes. This is from heat waves, from wind, and compare it to the 10-year and the 30-year averages, you can see they're quite large. And it's not just in the U.S. In Russia, fires, the smoke in Moscow in 2011. Over in Pakistan, the floods in that part of the world. And so in 2011, overall we lost $148 billion. And of that, about $55 billion were covered by insurance. And you know who picks up that which is not covered by insurance. So these are huge losses for 2011. And then you can go into 2012, snows in Rome, very unusual. Ice in the canal in Venice during the winter. A severe winter in Croatia. Then coming into the summer seasons, the droughts that we hear about now, and have intensified. 60% of the U.S. is in drought. That hasn't occurred since we've been keeping records since 1895. And this shows where they're most severe across the country. And of course, along with that, we've had record temperatures. And we can just look at March in 2012. These are departures from normal. You can see much of the U.S. is over 8 degrees Fahrenheit above average. And there were 15,000 warm temperature records broken in the U.S. in March alone. So these are huge changes. And again, this is global, the flooding in the Black Sea in 2012, the fires out in Colorado. And you wonder, when you look at this, and well, maybe B.F. Skinner again is right, consequences for the individual outweigh consequences for others, because individuals are now being impacted. And whether this will change the opinion of the public remains to be seen. And then just in the last couple of weeks, up in Greenland, the red areas show them where the melting was occurring on July 8th, and 4 days later, on July 12th, all of Greenland, 97% of it is melting. And is that unusual? Yes. You can look at an ice cores and go back and see melt layers. The last time we had them were 1889. So it is unusual, but not unprecedented. So it is not this is an evolutionary theory. It says it is not the strongest of the species that survive, nor the most intelligent that survives. It is the one that is most adaptable to change. And that is evolution. But individuals, groups, and nations, in contrast to evolution, can understand their circumstances and deliberately make the appropriate policies for a change. Evolution doesn't allow that, but if you're a thinking, planning group of people, you should be able to actually do that. So there's a perfect storm brewing, and the ingredients include the fact that CO2 has this lifetime of over 1,000 years. The climate system has an inertia. We will not see the effects of the CO2 in the atmosphere today for 20 to 30 years into the future. That's because it takes a long time to warm up the world's oceans and melt the ice sheets. There's a positive amplifying feedbacks. When you melt ice, you expose darker surfaces, more energy is absorbed, so it pushes the system. And we have a fossil fuel addiction around the world. And we can talk about the alternatives, a brighter future, cost-free fuels like solar, the clean air and water, economic development and good jobs. And I think we forget that in this country, this day, there are only about 80,000 coal miners. There are over 100,000 people working in solar-related energy fields. So I think this is the future. So what can we, the audience, do? Little things and big things. I think that some of these changes that are already underway include conservation, increasing efficiencies, people buying hybrids or smaller cars to get better mileage. I think the renewable energies such as fuel cells, zero emission coal burning power plants, we haven't come a long ways on that, but the technology is out there. Solar, geothermal, ethanol, wind power, these are all part of the solutions for the future. We can look at mass transit, light rails, buses, housing design toward more compact cities so you don't have to drive so far. And then the nanotechnologies and LED technologies, these will all be good for the future. And what you can do personally to actually save some money, buy organic foods as much as possible, avoid the heavy packaging products, eat less meat, reduce the number of miles you drive, carpool, keep your car tuned up, keep your tires properly inflated, choose fuel-efficient vehicles, try car sharing, where you have one car between 3 or 4 families, fly less. These things that you can do, but this is not enough. I think the only way you will change the track that we are on, it's not by shopping, it's not by recycling. All those things help. They're very important to do them, but it is by being a good citizen, because we have to change policies at the government level in order to make a change on the track that we're on. So big ideas, change the system. We need a new economy towards sustainability. We must work together, because the problem can't be solved by individuals or groups or political parties. I think that this time around will require a public awakening, and the question is what that is. Maybe what's going on in the natural environment right now might do part of that. Establishment of political will, well, this is voters, and if people want to change, they can bring about a change. Resetting of priorities, I think that's extremely important. And there will be some sacrifice for the future. I think that comes without saying. And I think there has to be an alliance of governments, businesses, and citizens in order to make progress on this front. So if I was asked what are the greatest challenges of the 21st century will be, learning how to get along with each other. We've been doing that more or less, and you can question how well we're doing it. And second is learning how to get along with our planet. And these two challenges deal with human behavior, and they are closely related. So I think these are the big challenges of the 21st century. And I'd like to go back to this view of the world from space, because I think one thing we've learned from all of our international space programs is how unique this planet is, on which sustains the life for all of us. And I think we have to realize that it's at risk. And when we look at the issue of global climate change, one of our big problems is nature's the timekeeper on these changes. And none of us can actually see the clock that we're working against. And therefore, I think we have to, at all levels, do everything we can as human beings to bring about a change. And that human behavior is a very important part of that. So thank you very much. Thank you.